In this video, we're going to work a problem where we find the components of a force along random directions. We're going to do this graphically. In most cases, you'll have a Cartesian coordinate system, so in either 2D or 3D, you can represent your forces and directions with components and use the dot product to get components of the forces along any direction. But it's still valuable to work practice problems with vectors graphically. You learn a lot of the geometry involved in working with vectors. Also, even with a Cartesian coordinate system, if you're resolving graphically along random axes that aren't perpendicular, then you still may need to use the law of sines or law of cosines to get information. So it's good to practice working with the law of sines and law of cosines and analyzing triangles that aren't right triangles. All right, let's get started. So it says the component of force F acting along line AA is required to be 30 pounds. Okay, so the component of the force along this direction is required to be 30 pounds. Determine the magnitude of F and its component along line BB. So if FAA, the component of F along AA, is required to be 30 pounds, then what does that mean that the component of the force is along BB, as well as what F is? So FAA is 30 pounds. All right, now to do this graphically, what you do is you go to the tail of the vector that you're interested in resolving and then walk along the axes to get from the tail of that vector to the head of that vector. So let's draw the axes at the tail. So that's AA, and that's BB. Okay, so the component of F in the AA direction is going to be going this way, right? You can see that. And then in the BB direction, it's going down here. So we're going to be going some amount this way and then some amount down. So if we go to the tail, or to the head of the vector, so this is at the head of the vector, and just extend this out. So there you go. To get to the head of force F from the tail, walking along those directions, you have to walk here and then here. So the length of these lines, FAA, the length of this line is 30 pounds, is 30. Okay? We don't know the length of this line, and we don't know the length of this line. Okay, but we know this angle is 80 degrees. To solve for the unknown angles and side lengths of this triangle, we're going to use the law of sines or the law of cosines or both. And so we're going to need one more angle or side length. So what can we use from geometry to get another angle? Okay, so we've got two parallel lines here, transversal, so opposite interior angles. This is 60. And so if we take 180 minus 60 minus 80, we get 40. So this is 40. So we can use the law of sines and say that 30 over sine of 80, right? Like it's sine of this angle over the side length across from it, or the side length over the sine of that, or the sine of the angle across from that side, is equal to, so then we'll say F. So F over sine of 40. So F is equal to what? 30 sine of 40 over sine of 80. Okay, so 30 sine of 40, we're in degree mode here, divided by sine of 80. 19.6 pounds. Now, this is a little confusing because you typically think, well, the components of something are always going to be smaller. I think we're so used to having our force be the hypotenuse of a right triangle. But when you're resolving, getting components along random directions, it just depends on the, you could be creating a triangle where of your main force is smaller than the other side lengths. So that's F. Now, what is FBB? We're going to use the law of sines again. Sine of 60 over what's across from that angle, which would be FBB, is equal to, we could just we just pick whatever we want. Sine of 30, no, sine of 80 over 30. So FBB is equal to sine of 60 over sine of 80. Okay, 30 times sine of 60 divided by sine of 80. 26.4.